Yeah, there were two questions in the break that I was asked to, that I could sort of try to answer again. One, very good questions. One was this document with the squares, how do I get there? Yeah, and it is indeed, it's somewhat hidden. And I don't want you to sort of memorize the URL. What I try to explain to you is how I get there is from the CRAN landing site. So I assume you know how to find SF on CRAN. Yeah. So I typically Google for CRAN package name, and that works 99% of the time. Unless people, you know, choose crazy package names, stars or so. Stars, CRAN. Even that works, yeah? Anyway, so simple features for R on CRAN side, then the CRAN landing page has a URL. The URL is the GitHub page, so where the package is being developed, yeah? So there are all the issues and so on. There's a lot of discussions, a lot of nice stuff to read, but it also has, let's say, a title and a URL, yeah, that is sort of directly here, directly sort of description. Okay, this is the simple feature for our package, and this is the URL for the package. And that's a URL that is not on the CRAN side, so you need to fetch that from the GitHub side. Yeah, it's our spatial GitHub IOSF, and that is where this package down documentation is. Yeah, and that is something that I think it's auto-generated, although this still doesn't work entirely sort of the way we would want to, but in principle, the idea is that anytime I push something to the GitHub repo, that this whole documentation is automatically regenerated and pushed to the website. So this is up to date with the development version on GitHub. Yeah, this is not up to date with the CRAN version. Yeah, so there's slight differences. And then you find, under articles, you find the 6 vignettes, and under reference, you find the pages for the individual commands with examples and inline graphic output from examples. Yeah, so I think that is one of the biggest advantages of this, really. Of course, the alternative is that you sort of look at section, that you look at the documentation here. Yeah, so this part that is relevant when Y is missing, and that you run examples online here and you see them happening. Chuck, 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 chuck. Yeah. So you can also do this simply by calling example of the command, and then the examples are being run in your interactive R session. So the gains are not that dramatic. Yeah, it looks very nice, but it's not like it's something we couldn't do. The other question was this. Where am I? Yeah, the other question was this. Like, okay, these 4 points. How do I get there, or how do I get to these to the selection of the counties that touch other counties in the point? And the critical thing here is that I'm doing a join by STRook. I'm doing a join with this pattern. Yeah, this is the pattern I'm looking for, and the question is how can we read this pattern? And that takes a while, right? That took a very long, because it is these 9. You have to go through these 9 things by rows, and you have to know that the first argument is here. Yeah, so this is not sort of, I find that equally hard to memorize as what is extensive, what is intensive. But what it means is Well, a star means that doesn't matter. Yeah, so a star means anything, irrelevant. F means false, means not intersecting. 1 means an intersection of dimensionality 1. It should be 0, right? Ah, that is why we have the 0 here. Yes. Okay, so the rook. So this is the rook stat. Rook is sort of what the movement that a rook can do, right, in the chessboard. So that is going up or going to the right. So that means we have, if we have a checkerboard, we have the rook neighbors are the 4 neighbors up, down, left, right, right? So we have a one-dimensional. Boundary between the two fields. A queen neighbors can do diagonal as well, so they can also have a 0-dimensional connection. So this means in the interior of the first and the interior of the second geometry do not intersect. Yeah, so we have no overlapping. We do not. The interiors do not intersect. Then the interior of the first with the boundary and exterior of the second one doesn't matter. Then the boundary of the first and the interior of the second doesn't matter. And then comes the important one, the boundary of the first and the boundary of the second. Yeah, they should have dimensionality 1 to get the rook neighbors. Yeah, and rook neighbors are things where I have a line and not a point. So I'm touching along a one-dimensional structure. This came up earlier, and this is another question, like this is the question, where do two states touch each other in a point? So that's a similar question, except that we don't want to have the boundaries of the first geometry and the boundary of the second geometry touch along a one-dimensional, along a line, but we want to have them to touch in a point. Yeah? So we replace that by a 0, and we get the point-touching counties, pairs of counties that touch each other in a point. Yeah, so they shouldn't. So here we exclude the self-intersections, yeah, because we offer the set of geometries twice. Yeah, we don't want the self-intersections, and we want to have the cases where the boundaries only touch in a point. And then we get some duplicates because some of the states do this twice, like this state does it with this state and does it with this state. Yeah, so that will end up twice in the list, but it doesn't matter if I only plot it. So that was the second question on how does this ST relate magic actually work. It's pretty powerful. Okay, so then we were here, and there was this. There's a list of functions that manipulate the geometries, that do stuff with geometries. A lot of these functions are simply functions that are available in GDAL and that are useful for some reason. Line merges lines, segmentizes lines. Why would you segmentize lines? When do we do that? One reason where I do a lot of segmentation of lines is when, sorry? For smoothing, yeah, but the thing is that we segmentize straight lines. So we have a straight line from this point to this point and add points on the line. So it doesn't smooth, it's just additional points. It's points you would leave out because they're redundant.
You can give different attributes to one line.
Yeah, but that's another chapter, that's the attributes, right? So no, I do it all the time when drawing graticules. Right? Graticules are these curved lines that follow constant latitude or longitude values. Yeah, so in principle they go from one side to the earth to the other. But then if you project them and still want to sort of follow that line, you need to add points along that straight line, right? And depending on how many points you add, it gets more complex. But if you don't add enough points, then certain projections will do crazy things. We've seen a lot of examples actually from people doing stuff with crazy things. So the graticule function, this is also one of the functions that I really, enjoy every day that I don't have to go back to that function. But this function takes an indiscrete, yes, which says like the number of discretization points of every line. So it's a bounding box and so on, and then it will sort of do a finely segmented line, because you're going to create a reticule in latitude, longitude, xy, and then you're going to transform it, right? And then you want to have it as a smooth curve, right? That means that you need to have enough dense enough discretization, and that can be controlled. But that is very hard to predict. It's hard. Voronoi diagrams, ST centroid. Centroid is one of these things is useful, and you can see it as something that operates on a geometry and that returns the centroid of the geometry, right? So it's kind of the middle point of the polygon for some definition of middle point. And we see that if we look at the centroid function, that it has methods actually for SF objects, for geometry list columns, and for individual geometries. Yeah, so I can apply this, can compute the centroid of an individual geometry, or of a whole geometry list column, or of a whole feature object. Yes, and if I do that for a whole feature object, what would it do? Of course, it will replace the polygons with their centroid, right? But what will it do with the attributes? Let's see what it does with the attributes. Do we have an NC here? Yes. So if I have the centroids is centroids of the geometry and see everything is fine. Yeah, plot CT. I see the centroids of these polygons. Yes, plots. I'm sorry.
Any of the options to make sure that the centroid is inside the polygon, or?
I don't think. Let me see. I remember being bugged about this. Centroid, here is an option of largest polygon. If you set that to true, you'll get the centroid of the largest polygon of a multipolygon. Yeah, so if you have two polygons of equal size, the centroid will be in the middle, will not be in the polygons. Yes, if you set this option of largest polygon, it will pick the largest polygon of a set of polygons and return you the centroid of that polygon. So the answer is yes. Look into the documentation. So this works on the geometries, but what happens if I do this on the simple feature object? Yes, I want to sort of compute it not on its geometry, but on the whole thing. What we get there is a warning. It says this warning: ST centroid assumes attribute are constant over geometries of X. Yes, that is because what we get back is, again, a simple feature collection which has all these attributes. Yes, but which now has, let's not plot all the attributes. But which does no longer have polygons as geometry, but has points, the points of the centroids, right? So now we see this thing, area, which supposedly has something to do with the area of the county. It doesn't, but in the wrong way. And we see other thing like the number of people that had this disease in 1979 associated with a point. Yeah, but there is no point that has an attribute like this associated with it. Yeah, so we're replacing the polygons with a point, and then we're gluing the attributes on it. And that is essentially, for most of the variables, the wrong action. For some variables, it would be kind of okay if we would have like the state name, the county name, that would be still the county name on that point. But not in a way that this point is that county. Yes, it's the county that this point is in. Yeah? So there's a change of relationship. On the other hand, if we would have like a variable like land use, we would have a polygon with land use forest, right? And we would compute the centroid, and the centroid has then forest. That's okay. Yeah, so there are different relationships we can have between attributes and geometries that sometimes lead to problems, yes, and sometimes lead to okay things, and sometimes lead to okay-ish things when we do these operations. When we say we replace a polygon with a point, like a point in a polygon. Do a point in a polygon and query the attributes. Yeah, that sometimes works. And so there is a little bit of infrastructure in the SF package that is somewhat underused, and we have to write it down better. It's an attribute called the AGR, the attribute geometry relationship. Yes, and that's a factor, and that has a value for each of the attributes. And right now we see that it's all NA, and it's a factor, and it can have 3 values. We can have the value constant. The constant, we can think of something like land use, which is sort of everywhere the case in this polygon, or something that's everywhere the case along a line. We can have aggregate, which would be something like area, or that would be something like population or something like that. So summary values that are not okay to be associated to a point. And we can have identity, where we have a one-to-one relationship like county and its name, right? So we have the county name, which is identity of this polygon, but not the identity of this point. But then for this point, it's okay. So you could say it's okay there. So we can set this attribute. We could say, well, if we say all these, we just make the assumption all these variables have the constant property, yeah. And then we compute the attributes, and we don't get this warning. Yeah, we can also say, well, these things are aggregates, and then we get this. Yeah, we get this warning. Yeah, we are assuming they're constant. Yeah, by assigning these attributes to these points, we make this assumption. Yeah, and this is something that is sort of interestingly. Something that I haven't found a lot about in GIS or spatial analysis literature or other GIS implementations. It's really kind of, when you work with geometries and with attributes, that you can have different relations, different semantics of how the attribute value sort of is associated with that geometry. Once the geometry is larger than a point, is more than a point. Yeah, when the geometry is a point, of course, it's all the same, right? But when the geometry is 2 points, or a line, or a polygon, it's really a difference. Yes, and it's kind of somewhat my background in geostatistics, where we work a lot with estimating aerial means for block region, something you cannot do with random forest. Where is Tom? It's a very useful technique that you cannot change of support that you cannot do with machine learning methods. Where you get aggregates, and a lot of things are aggregates, right? The area, the population data, almost all socioeconomic data is aggregate data for geometries. So if you see this warning, then you can avoid it by setting, making the assumption explicit, and setting this attribute geometry relationship with the st_agr function. It's also described in one of the vignettes. There is polygonize, simplify, split, buffer, make valid. Make valid is extremely useful. A lot of polygons are not valid. Make valid tries to make them valid in some kind of magic way, and people use it. If you have invalid geometries, you're just, it might be your friend. Other things sort of manipulate the z and the m. Quite often, if you get geometries with z and m, you want to drop them or so. Then we have handling of the mixes. So I mentioned yesterday that we can have geometry collections. Here is this graph again where we get one. Sort of when we intersect this red polygon with the black one, we get the intersection, which is a single geometry consisting of a point, a line string, and a polygon. So that can only be sort of collected together in a structure called geometry collection. And then we get an SF object that essentially has geometry collections. Yeah, so we get them. Yeah, so let's see if we see one of them. Yeah, we see here we get this geometry collection. We work only with simple singular geometries here. So you can see the point and the line string and the polygon coming out of that. And then the question is always like what to do with that. And there are ways of getting out of that. For instance, sometimes you want to sort of move. Here is the function Stcast that tries to cast, so that tries to sort of mold one geometry type into another one. Sort of, this is extremely simple if they have the same representation, like multi-point and line string. They're both matrices. We can just change the type. If we have like a multi-polygon and want to move that into a polygon, we have features, then we basically we increase the number of features, right? So we get 2 polygons instead of one multi-polygon of two rings. So this is, somewhat helping sometimes somewhat, and sometimes it isn't. Here we have so one option, one possibility is that you have like a mix of geometry types at the single feature level. Yeah, so you have a single feature level, you intersect 2 geometries. You get a single feature geometry that is a mix of types. That's a geometry collection. The other thing is that you do something and you get a set of features back, and that this set has different geometry types. Yeah, so the first feature is a point, the second feature is a line, the third is a multi-point, and the fourth is a polygon. Yeah, so that also occurs. And what you then get is objects that have as their sort of geometry type of the, let's say, of the geometry, have type geometry, yeah, which is the superclass. So it's a mixed bag. So here we have one created. We created one by combining a point, a multi-point, and a line string. The point, the multi-point, and the line string. And we can put them together in a geometry list column, and that then has geometry type geometry. Yeah. So that's also not nice. Yeah. That's the other type. So there are 2 types. One is at the single feature level. The other one is at the set of feature level. Single geometry collection, set. We end up with geometry. And in both cases, you want to do kind of stuff. You want to sort of get your way out. And select by dimensions, forget all the one-dimensional things, and we get a line string out, and then we get an object that has line string. So we basically cut out things, or we're trying to mold all of them into a single structure. Like here, we could mold all of them into multi-point, and this first point is a single point multi-point. The line string is then converted into. The line string is then converted into a multi-point object. Yeah. Not that that is good, but it is sort of, you typically want to sort of find your way out of that. Empty geometries, as I mentioned, these are empty geometries just to make the whole thing consistent, and there is a function isEmpty that allows you to select them. It's like an NA value, but then an NA for geometries, and as I said, the funny thing is that they're typed. So every sort of every thing has a representation, and a bad thing is that the empty point is implemented here as length 2 vector with NAs, unlike anything else. And this is not sort of the standard, the simple feature standard doesn't really give an answer of how to do this. This is an omission of the standard, funny enough. And so this is an omission that makes you have to work around empty points and all kind of interfaces to libraries, because the standard doesn't tell what to do. So you don't know. Okay, then we have a very short section here on tidyverse for those of you who really like tidyverse. I mentioned yesterday there's a couple of functions that where really sort of SF adds something, does something in particular. In particular for summarize, I mentioned, it will sort of create new geometries by unioning the geometries that we summarize. So summarize sort of summarizes records, or summarizes features in our case, and then the SF variety of that also merges, unions their geometry. We see here, this looks terrible. I was reading this and I couldn't, this section, and I really thought, what is going on here? But this is apparently a way, I didn't understand it, but this is a way to find out the tidyverse methods that SF adds. Yeah? So here I'm grabbing the functions, yes? Sorry, the methods that the package offers for SF objects before loading the tidyverse, yes? So now we have this set of methods M1, and then I load the tidyverse, and then I again ask all the methods for FSF, and then I ask the difference between these two sets. Yeah, so after loading the tidyverse, we basically get this set of methods that has particular methods implemented for SF objects. So that is quite a handful, like 24 methods. I don't know what they all mean. Most of them simply pass the work on to dplyr, where most of these things live, and get them back and put a geometry back to, because we work with sticky geometries. Here's a couple of little workflows where we sort of summarize densities of populations for larger regions. Basically, we cut sort of North Carolina in 4 sections, where we say, well, cut longitude by 4. Here we get the coordinates from the centroids. So we extract the geometry list column. We extract the centroids from that. We extract the coordinates from that. So that gives the 2-column matrix. This is this first column, so that is longitude. So we cut things by longitude here. So we added longitude, and then group by sort of the cut of longitude in 4 parts, and then we summarize we get a new variable called area, and density. So we sum the area, and then we compute a new variable density by the summed birth in 1979 divided by the area. So that should be a proper density over these larger areas. Yeah, we sum the area, we sum the persons, and then we compute a new density from the summed values by averaging this. I don't know if it's correct. Nice. And then we ggplot it, and here you see the ggplot again with the nice graticules and so on. Good, that was basically it. So I had a couple of notes here about rasters and things, but that is not really sort of very actual anymore. I told you more about it yesterday, that was essentially all I wanted to say about the simple features package. So now we can ask some questions. And otherwise, well, let's see if there are questions or remarks or more generic questions about life, the universe, and everything. Yes, oh, good.
I was asking about the simplification of the geometry, but by ID or by subdivision of the area, not like by the whole area?
I think there is an ST simplify, and I think it only does line simplification for individual geometries. So let's see what ST simplify does. So it will not help you much. So we have simplify. It has a very hopefully, it has a preserved topology flag, which is false, which you could set to true. But what it does is it simplifies a simple feature geometry and then goes to the next and simplifies that one. So if it says preserved topology, it means that I may have a certain multi-polygon that has a certain topology and I preserve that. But if I have like two geometries, counties with a shared boundary, then I will not do that because they are two different features. I will go to the first county, simplify that, go to the second one, simplify that, and you will see that the boundaries don't match up anymore. So you might be lucky, yes, but you know, we didn't run out of luck in this world, but typically it doesn't do this on a sort of on the set level. It does do this on the individual feature level. That's how it's implemented. And the parameter you need to pass is the tolerance, which is the tolerance parameter is specified for all or for each feature geometry. So you can do that on a feature-specific way, but typically you don't. So let's try to simplify and see. So what are the units here? Meters. Let's simplify this by, I don't know, kilometers or so? I have no idea what will come out. 10 kilometers. It doesn't do much, but I didn't say any. I had to say, of course, the tolerance. Yeah, here we see some serious simplification going on. Yeah, so welcome to the mess. Yeah, so yeah, so that's what it does. Are there any other questions? Good, then I suggest that because we have some more time, like 1 hour to go. So I suggest that we sort of work on the exercises now, and maybe I can like, do that for 20 minutes, and then I'll do a 10 minutes break in which I go through the answers to the first half, and then we do another like 15 minutes, and I take 15 minutes for the answers of the second half. Yeah, so that you can sort of come up with questions and so on in the meantime. Yeah, let's do that. Good. So let me just sort of go through the first 5 answers. I tried to answer them with RStudio. That was convenient. And there's a solutions.rmd file that you find in the repo. So if you want to go through the end and load it and run it, you can do it. So what I did, first question, for each of the datasets, describe which geometry type it has, how many features and how many attributes it has. So I was just sort of printing essentially these 3 objects, yes, and then you can sort of, from that you can read how many features, how many fields are attributes. And so breweries has 24 features and 8 fields, and has geometry type points. Yeah, so breweries is points. The second one, and here are the points, The second one was Trails. So Trails has 543 features, so 543 trails, 3 fields, yeah, so 3 attributes, and is of type multi-line string. Yeah, so each of these things is a multi-line string. You can see them here starting, coming, and here you can see the 3 fields they have. So name and some kind of code and the district they're in. And then the Franconia has 37 features and 7 fields and is of type multi-polygon. Yeah? So they are administrative regions with a nuts ID, with a shape area, shape length, and a country code and the name of the area and a multi-polygon. So that was the first question. So you can print these objects and you read that from the summaries you see. Then plot each of the 3 objects. Yeah, well, it doesn't plot everything probably, but what you get is the points plot, whatever it's worth, because you don't see any reference. You can plot the lines, same thing, you don't see the real reference, and you can plot the regions. So, of course, a better plot would be to use the reference of the line. Do I have them here? To plot the reference of the Franconia. I think like this. Oh, this looks terrible. But in any case, and then plot the geometry of the breweries on top of that. Let's see if that works. Yeah, so it kind of works if RStudio would be more friendly to. Here it's zoom and it looks good. Yeah, so at least then we see breweries in the context of the in the reference, in the context of the regions, yeah, which for this combination works. Then we get the next question. Export Franconia to a GeoPackage file. I used write.sf for that. You can also use st_write for that. I used write.sf because it overwrites, and I ran this a couple of times. So this runs. And then I opened it in QuantumGIS. Let's see what happens if I double click. No. So this might be a very old QuantumGIS version, I now realize, but I don't know why this is. So here it is. It looks different. I don't know why. Is this because it's plot carré or so? It looks like squeezed. Does it? Or is it the same plot as we saw? It's different. It's sort of stretched. And here it's not stretched. Here it's squeezed. Does this use plot carré? Like, does it use the same scaling for latitude as longitude by default? That would be stupid. Anyway. This is not how things look like. So anyway, this is what QuantumGIS does.
It doesn't recognize them.
Can I not ask for things? Here I can ask for all kinds of properties with the queries button. I get all the. Here it says EPST 4326. Okay. Yeah. So it looks like it does plot carré, meaning that it linearly maps both latitude and longitude to x and y, which makes sense for areas around the equator, but not so much for areas of this size, at least in my opinion, but then opinions differ. RStudio. Yeah, so we opened it in QuantumGIS. The next thing is compare the coordinate reference systems of the 3 objects. In case of different coordinate reference system, convert all of them to a single CRFs. And it didn't tell you which one. But this is what you can do. Here, ask for the CRS. So you can also look at the summaries where it's also printed. Yeah, in the summary it's also printed. We see that the EPSG is, the ID is this number and the proj4 string is this, so you can also compare those. You can also ask them here explicitly with stcrs, and you get the three sort of, things printed, and we see that the first two breweries of Franconia are longitude, latitude, WHS 84. And the third one, Trails, is in UTM. And then what I did is create a new Franconia UTM by ST transforming Franconia to the CRS of Trails. Yes, and create a breweries UTM by transforming breweries to the CRS of Trails. So I'm going to move to UTM, but you can also move Trails to latitude, longitude, and then you have three things in latitude, longitude. And then you can continue working with that if you do distances. Yeah. Okay, so in 15 minutes I will continue with, was that question 5? No, this, the numbering is false. I think question 5 was, for each of the trails, find out which brewery is closest to the trail. Yeah, there we start with spatial analysis. It gets nasty. So the way I did that was computing all distances with ST distance. Yeah? You did that too? Good.
With ST distance, which one? Yeah. And use an apply function to find the mean.
Use apply, right? Yeah.
Yeah. To find the mean for each row, because it gives you a matrix of
Right.
of rows and columns, which is
Yeah.
yeah.
That's what I did. So this gives you
exactly.
a distance matrix. So it has a number of rows of 500 something, the number of trails, and number of columns equal to the number of breweries, which was how many?
500 something.
220.
220 breweries. So this is this will be 520 by. So we see it here. This is the the first 5 by 5, sort of the upper left corner of this, of a very large matrix with distances. They're in units, meters, because I worked with UTM. But anyway, it will be units, meters. And then you need to find out for every trail. Well, trails are rows because this is the first argument. So for every row of the distance matrix, you need to find out which column has the smallest value. And that's a tricky one. Yes. So there is a function that does that. That is called which.min, and that tells you what the index of the smallest value.
I have done this in a for loop.
In a for loop,
Yeah.
you computed the minimum and then looked it up.
I didn't know this function, so I had to do it in.
So that is the other one. If you don't know about which.min, you need to write a function that does which.min. Yeah, but this is such a common thing that there is a which.min that does that. And apply is something. We're now we're now leaving the comfort zone where you were in the data frame world, right? And we're entering the world where we look at pairs, right? Pairs of things. For instance, all distances between all the trails, all the breweries, is a matrix. Yes, and matrix are very uncomfortable if you like to live in Tidyverse or in data frame world. Yeah, but it's a powerful thing because it has everything, and we just have to go through the rows. And apply is one of these functions that it's functional programming. So you basically apply a function to each row. Apply takes an argument 1 that means do this over the rows. I can also do it over the columns. If I say apply matrix, 2, then it will apply something on the columns. And then you give a function, which.min, and that sort of which.min gets the first row and gives back the index, gets the second row, gives back the index, the third row gives back the index. So you get a vector back of the indices of the, and I printed here the first 5, the indices of the nearest brewery for the first trail, nearest brewery for the second trail, nearest brewery for the third trail, and so on. This is one way to do it. There is another one, but this is a fairly new feature of SF that is not yet, probably not in your version yet, but if you would install from source and from GitHub and so on, you would be able to use the ST_nearest feature, which is...
Can I just... I was trying to cheat with this function, but I couldn't load it. It was I found it, but it didn't like...
No, it's not. ST_nearest feature is not yet on GitHub.
Okay.
It's on GitHub. You need to install from source, then it would work. And it also needs to have GEOS 361 as a minimum, because this is a fairly new thing in GEOS. The nice thing about it is that it doesn't need the distance matrix. Distance matrix, you will notice that it takes a while to compute. Not because it is 200 by 300 distances, but it's because it's points to lines, and points to lines is a pretty complicated operation, right? It's really sort of finding the shortest distance from the point to the line, which might not be a node in the line, right? So it does the whole geometry there, yeah? So the distance, the ST distance takes time, and sort of nearest feature doesn't take time. It's sort of instant, but it will be in the next version. And interestingly, we see that the first 5 records are the same, but if I sort of compare them and sort of look at the table where I sort of look at which ones are identical of the nearest features and my apply method, then I see that there are quite a few differences. In 32 out of 540 cases, they are false. These are the records that are false. And then I checked something. Why is this not being printed? Yeah, so let me do this. And then if you check, for instance, record 181, yeah, and you take the distance of 181 and look at what the answer was using the apply, what the answer was using ST_nearest feature, you see that we end up with 2 breweries that have the same distance to the feature. Yeah? So the nearest, which nearest is an ambiguous question. Yeah? If there are there can be multiple answers if there are multiple breweries having the same distance to.
Probably because they're duplicates.
They're duplicates, yeah. So this happens. So this is always something you need to be aware of. If you do distance selections, do the so many nearest or the nearest neighbor or so, that might be ambiguous. So far for answer 5, and so in 10, let's say, in 10 minutes I will continue with the rest of the answers. Okay, so anyone managed to answer question 6? Yeah? How? From the distance matrix?
So I just used the answer from question 5 and then used that to index the breweries and did ST distance to calculate the distances between them.
Okay, yeah, that's an option. So we kind of queried them here by doing this, sort of querying the object with, with sort of finding the nearest, which index it was. The alternative would be to, instead of which.min, to just apply the function min to the rows. And you get a minimum distance value back. Yeah, but that's the same thing. Good. Right, so we are continuing to the next question. find out how many breweries it has that are less than 500 meters away from the trail, per kilometer of trail. Oh, if I did this per kilometer of trail. So what I did here is sort of, again, working on the distance matrix on the rows, because we want to sort of do something for all the trails. And I summed, I wrote here an anonymous function. You can also give the function a name and pass that function, but you can also define it on the fly, because all you do is basically compare the distance values with 500. Yes, if they are smaller than 500, true. You sum that. True is 1, false is 0. So you get the number of records for which this is the case. Yes, this is a sum of logical is the number of truths. So you get these numbers. But then I didn't do the whole question, right? Per kilometer of trail. So I would sort of add that to, like, save that in a variable n, and then sort of divide that by trails. Maybe st length trails. Let me see if that works. Yeah. So I get the number again here. This function gives this matrix, and then I save here the number as an object, and I divide that by the length, and I get something that in any case has the right units. Yes, it's 1 over meter. Yes, so number of breweries per meter. Did I ask for per kilometer of trail? Oh, I was picky here. No. So units, set units, kilometers. Yes. Okay, I get 1 over kilometers. Yeah, so we get sort of values of up to 2 breweries per kilometer, which is not so bad, within 500 meters distance. Let's just summarize that. Ooh, what happened here? So, the maximum is 22. That is a lot. But that will probably be these duplicate breweries, right? There's apparently a trail with more than 22 kilometers per kilometer within a stretch of 500 meters. That sounds utopian.
Outrageous.
Yes, outrageous. Yes, there is something going on here. The next question was for each of the regions in Franconia. Okay, so we're going to do regional analysis now, polygons, find out how many breweries it contains, and add this number as a field to the Franconia object. So I did here, I used st contains, yeah, and st contains, of course, gives you this nasty thing back, right? The sparse geometry binary predicate list. So you can either say, well, I'm going to move that to a matrix and do a sum of the rows. That is one thing. Another thing you can do is the function lengths. Yes, this is not a well-known function. The function length is pretty well-known, gives the length of a vector. The function lengths gives the lengths of all of the vector elements. And since this is a list with indexes, yeah, so you want to sort of have the length of the first set, the length of the second set, length of the third set, and so on. You can use it directly to that extent and run that, and you get these. Yeah, so I just picked the first 5 elements, so you see how many the first 6, how many the first 5 regions in Franconia, how many breweries they have included. And then I added this whole thing here as a new record that I can then, do something with it. Yeah. And I get this warning here because I'm working on Franconia and breweries, and it says, although coordinates are longitude, latitude, ST contains assumes that they are planar. Yes, I'm doing a ST contains, and ST contains passes things to geos, and geos works with Cartesian coordinates. It's a 2D software, right? It's not spherical. So we don't do contains here on the sphere. We do it in 2D. And that works okay most of the time, unless you're in polar regions. Yeah, there it does not work okay. Yeah, and or massive regions or whatever. Yeah, so you always will see this message because it's hard to tell from the outside whether this will be a problem or not. So if I would do this on the UTM, Franconia UTM, and breweries UTM, I would have been saved. Yeah. From that. Yeah, so I don't see this warning message anymore. Yeah, it's gone. And I know. Can put it back in the old thing. Okay, yeah, so I still have to hear this. UTM, let's be consistent. Yeah. Gone. And then the one but final question. For each of the regions in Franconia, count the total number of types of beers brewed by all the breweries in the region. So instead of just looking how many geometries, how many breweries we have in each region, we now look at a property of the breweries. Yeah, the brewery brews a certain number of beer types, and we want to have the total number of beer types brewed by all of the breweries in the region. Yeah, so we want to have the geometry, and then have the attribute, and sum that attribute. Yeah, that's what we do. So we work on breweries. Yes. Oops, what happens here? We work on breweries and basically on the attribute number of types, and we aggregate that over Franconia. And the function we use to aggregate is sum. Yeah. So aggregate takes a thing you want to aggregate, the breweries, with the number of types as attribute. Aggregation predicate, so that is here a spatial thing, so it's going to group things by these spatial regions, and then a function to apply to the attribute, the sum function. And then if we do that, interestingly, I looked at this for a long time, and then let's do everything upstairs, and then let's run this thing. So if we do it like here, let's see if it's still here, then and we plot A, then we see that most of them are empty. Yeah, but this is not what we saw when we plotted the breweries up top of the stage. The breweries are everywhere, right? So something went wrong here, and then you need to sort of find out what is going wrong. And you could sort of look at what breweries number of types has, and you see that there are 151 breweries that do not have the number of types field filled, yeah, that have an NA value there. And if I do a sum over something and an NA, then I get back an NA. So I get a lot of NAs back because they propagate. Yeah, so this happens always in R. Whenever you do something with NAs, unless you take care of the NAs will propagate, which is in general good, but not really what we wanted here. So what could have gone wrong? I'm looking at the variable, I see these NAs, and I think, okay, I'm doing a sum, but I need to remove the NAs, yes? Sum has a parameter NA that remove is false. If I set that to true, I can just add here parameters for the function sum. They will be passed on to sum, then it will work, and I get this plot, which looks much more healthy, much more sort of where the breweries were, right? We still see NAs, the white areas where we have a sum of nothing, I guess. That would be 0. Yeah, so this is something to check out, what the white areas are, right? I think they are zeros, but that's never believe what you think. Then the last question is more tricky. Count the total length of trails per region in Franconia. So we're doing now an intersection of Franconia, UTM, and trails. Yeah, so we cut the trails by region, right? We get all the pieces of trails organized by region. I said here, this was my wrong approach. Why was this wrong? And I computed the length of everything, and then I said, okay, let's aggregate all these lengths, yeah, over all these regions and sum them. Yes? The thing is, what I then do is that I get too many matches, yes, because the way things are being put together in aggregate is by intersecting them. And so we get also all the trails that touch the region, but that they're not inside the region. Yes? Let me see if there is an... So this is basically because this is the default value for the join predicate of the aggregate method for SF object is ST intersects. Yeah, so this probably would have worked if I would have said join is ST contains rather than ST intersects. Now I get everything that intersects that's also lying outside the region, but touching it also intersects. But I took a different tour here. I said, no, I'm going to do a merge by nuts idea. Yeah, so I'm going to group by nuts idea and then summarize that. So I sort of cut up I merge all the trails by their nuts ideas that they have, and then sum their lengths, and then I do a left join based on nuts idea. Yeah, so here I merge Franconia with the nuts idea and length field of the table with all the cut up pieces of trails and their nuts ID and their length. It's very convoluted, yeah, but it was late last night and I couldn't think of I thought, you know, whenever it works, it works. There's 100 ways of doing this. So I did in any case, I did a sort of a left join basically on nuts idea, which also works. And then I did a check and said, okay, for all these join lengths, compute their length, total length, and compute the total length of all the cut up pieces of trails, and I ended up with so I ended up with 2 identical numbers, and then I was confident if these are the same, then they will probably be right. Which might be over-optimistic. I might have made the same error twice. That is another sort of not unusual scenario. Is there anyone who took a different path? So I think I would also have, I'm thinking aggregate with ST contains rather than the default ST intersection. Would have been much simpler. Let's try that. Hang on, the trail length is now And then I need to maybe something with. What's going on? Oh, maybe length has missing values in it. I didn't even check. So there was already a length, a computed length field here. Anyway, so this needs a little bit of messing around. I'm not going to solve spontaneously. So are there any questions related to this? So, I hope you enjoyed your first hands-on on doing, the GIS type, spatial analysis type of stuff with SF. So now you realize that it's not light, but whatever environment you would use, it's not light. When I would have thrown you, post-GIS to you and said, do the same exercises, you could do it, and you would get sort of different commands, but it's the same principle, because the same underlying data structures and the same underlying functions and mechanics and so on. Yeah, so that's good, and hopefully this worked out for you and motivates you to work with SF. If you have any questions with SF internals, then use RSigGeo or raise issues. If you think it's something with the software, then raise issues on GitHub. Yeah, that is also a lively sort of discussion platform where a lot of developers are involved. And otherwise, thank you for your attention. Oh, hang on, sorry. It's on GitHub. It's on the repo on GitHub. The user 2017 repo that I pointed you to. I was going to tell you how to cheat. I didn't. Sorry, but it's the answers are at least my answers as far as not the updated. I'll save the updated and push that to GitHub. Yeah. Okay, then it's time for lunch. Thanks for your attention.